So welcome everybody. It's a pleasure to have Yanu Khusanova visiting. Yanu studied Ural Federal University.
Yeah.
Then joined the Austromundus program, which allowed him to visit a number of institutes, including Rome, for 6 months. In 2016, they joined the PhD program at LAM, working with Olivier Lefebvre, and as part of the in the PhD program, she joined a number of galaxy surveys, including the Alpine Large Program. That was one of the biggest, first large program for extragalactic studies with ALMA. And since 2019, Yanu is a postdoc researcher at the Max Planck for Astronomy in Heidelberg, working with Eduardo Bañados. And today we'll hear about JWST science.
Yeah, thank you for the introduction. Thank you everybody for coming. I'm happy to present my latest work today, which is with JWST NIRCam observations of H-alpha emitters at redshift 6.2. But this program is not only for redshift 6.2, but this is the redshift I'm most interested in. And the reason for that is because this redshift corresponds to around 1 billion years after the Big Bang. And the first billion years is a crucial period of history of the universe. In the first billion years, galaxies and black holes grow rapidly, and the evolution of galaxies and black holes is also influencing the evolution of the universe. So after the end of Dark Ages, when the galaxies start to emit the first light, they reionize the intergalactic medium, and from neutral it becomes ionized, and this ends around 1 gigayear after the Big Bang. So this is a big phase transition of the universe, and in the same time, supermassive black holes grow up to the masses which are comparable to the most massive black holes at present day. So this is a very rapid process, and the big question which we are trying to answer is, how do these galaxies and the supermassive black holes grow so rapidly, and how the evolution of them is influencing one another? But if you want to understand how the galaxies grow, we need to measure the star formation rate in these galaxies. And there are many different ways how to measure star formation rate. And the basis of all these methods is on counting young, short-lived massive stars. Of course, the easiest way to count them is to look at the light which they emit in the UV. So UV can provide us the estimate of the star formation rate. But there is a caveat, and this is dust in the galaxy. Because of dust, fraction of UV light is attenuated, and therefore we need to account for dust if we use UV to measure star formation rate. Or we need to measure the infrared light, which gives us estimate of the light which is re-radiated by dust. Another way to measure star formation rate is to look at the emission from H2 regions around massive stars, and this can be done, for example, with H-alpha, but also other emission lines like Paschen alpha. And finally, we can also look at the interstellar medium and a C2 line, which traces ionized, neutral, and molecular gas in the galaxy. That's why it's a little bit different than H-alpha, which is only tracing H2 regions. And there are many more methods how we can measure star formation rate, but each of them has caveats, and they also trace different timescales of star formation. And before JWST, the most used star formation rate tracer in redshifts above 6 was UV. And in the infrared and C2, we could access these star formation rate tracers with ALMA and NOEMA, but this is difficult at high redshift, and we need a lot of time for one source, so it's hard to assemble a statistically significant sample, especially at highest redshifts. But JWST is changing the picture, since now with JWST we have access to H alpha, which previously was only accessible up to the redshift 2.5. But of course, we need to find these high redshift galaxies. And finding high redshift galaxies was one of the primary goals of JWST. That's why one of the first observations which were done with JWST was to observe galaxies with the CEERS Cosmic Evolution Early Release Science Program. And CEERS was targeting EGS field with a number of filters. These filters you can see here shown in blue. And complementary to these filters, there is also GST data. And with these broad filters, we can find high redshift galaxies using the most common dropout technique, in which we are looking at the Lyman break, because light below Lyman alpha gets absorbed. At high redshift, we would not observe the galaxy, for example, in this band, but we would observe it in the next band. So you can see that based on this flux drop, we can find high redshift galaxies. But the big caveat of this method is that the redshifts obtained this way are highly uncertain. And also, in many cases, low redshift, the highly dust-obscured galaxies can look like high redshift galaxies, but they are actually at low redshift. So if we want to have a truly high redshift galaxies, we also need spectroscopic follow-up, or we need another technique, which I will show here. And this is by adding a narrow band. With a narrow band, we can select galaxies which fall exactly at one specific redshift range. And this is because if emission line falls into the narrow band, then we will see an increase of flux in the narrow band compared to the broad band. And if we have a medium band, for example, here, we have this medium band at 4.1 micron. We can even further constrain the redshift, because in this medium band, we only see the continuum. So this is a very powerful technique, and it allows us to find H alpha emitters at redshift around 6.2 and O3 emitters at redshift around 8.4. But if we want to distinguish between these two line emitters, which look very similar if we look at the broadband spectrometry, we also need deep observations at around 0.19 micron, in which H alpha emitters would be visible, but O3 emitters won't. And so that's why in this NIRCam narrowband survey, we added these two filters. We added the narrowband to find high redshift galaxies, and we added the F090 band to distinguish between H alpha and O3 emission. And this band is deeper than the Hubble band, so it allows us to have better constraints on the redshift. And the program was designed in a way that we would find galaxies with star formation rates as low as 5 solar masses per year. But as I mentioned, we target a whole bunch of redshift ranges, and at lower redshift, we target lots of different emission lines, which some of them can also be used as star formation ray tracers, and there are a lot of low redshift galaxies, which look very interesting. We have some Paschen alpha emitters. We have some systems of, for example, here's bracket beta emitters. And we also have some low redshift galaxies with AGN, since here we can see a point source and the extended source. But I'm talking today about the high redshift. And here's one of high redshift H alpha emitters. As expected, it is much brighter in the narrow band, and it's not visible in the medium band and in the broad band. It's only have a very faint signal here. And it's detected in the F090 band as expected. This technique works. We can find H alpha emitters, and because we use a blind search with photometry, we can observe the whole area of the survey, and we can see where H alpha emitters at these redshifts are located. And what immediately catches the eye is that there is an overdensity of H alpha emitters. If we look at the morphology of these H alpha emitters, we can see that there are also a lot of sources with complex morphology. At bluer bands, we can see the morphology better. Here you can see that this is a double source, and the scale here is shown in yellow is 1 arcsecond, which corresponds to around 1 kiloparsec. So this is a very close and probably interacting pair of galaxies. And many other sources also have a complex morphology. If we look where they are located, we can see that most of them are in the overdensity. So we can see that in the overdense environment, there are more interactions between the galaxies. We can also look at the spectra of these galaxies. There are a lot of ancillary data for this survey. The most recent is the new spec observations from Rubis, but even before there were already NIRCam wide field slitless spectroscopy observations, and NIRCam wide field slitless spectroscopy is actually targeting exactly the pointings where we have this overdensity. So it's very convenient that we can look at the spectra of these galaxies. But compared to the narrow band, slitless spectroscopy is not so deep. So out of all these targets, only 4 of them have actually spectrum from NIRCam. And today I'm going to show you this spectra and what we can learn from this. So the spectra is very complementary to the narrowband observations, because we have H alpha measured with a narrowband, but in the spectrum we can also see the H beta line and O3 line. And as expected, the redshift of this galaxy is exactly where we expected. So actually all galaxies which have spectra are exactly at the redshift where they should be. But what is interesting about this galaxy is that based on the binary decrement, it doesn't have any dust attenuation for nebular lines. So this could be a dust-free star-forming galaxies. And this is one of the most star-forming galaxies in the sample. But there is another galaxy which is even more star-forming. And in this galaxy, we don't see H beta. And if we estimate the dust attenuation based on this non-detection of H beta and use it as an upper limit for H beta, then we obtain the result that the star formation rate of this galaxy can be twice as high as if we would only use H alpha as star formation ray tracer. So a lot of star formation in this galaxy is hidden by dust. And what is also interesting is that here you can see that there is another source very close to the main source. And this is also a galaxy at redshift 6.18. And it is also a dusty galaxy based on the spectral energy distribution fitting. But it is slightly less star forming as this one. Another example is interesting because this shows a signature of AGN. There were already a lot of discoveries with JWST of AGN candidates based on the widths of H alpha and H beta emission lines. And here again, we see a broad H beta line with the width of more than 3,000 kilometers per second. And this width of H beta line would correspond to the mass of the black hole of 10 to the 7, 10 to the 8 solar masses. But even a better example of AGN is this one. And the reason for this is because the redshift of the spectroscopic redshift of the source is just a little bit outside of the transmission curve of the narrow band. So the explanation for this, the best explanation for this is that either we see a broad H alpha emission, which is so broad that part of it falls into the narrow band, or we see a nitrogen line. And in both cases, this would mean that the emission in the narrow band is dominated by the AGN emission. And based on the morphology of the source, we can see an evidence for that, because in the broad bands, we can see a combination of extended source and of a point-like source, but in the narrow band, we mainly see a point source. So this is likely a galaxy with AGN. Also, the redshift is not very certain, because here you can see that there is a very good detection of all three emission lines, but H beta is not so certain. It could be just a noise peak. But if we assume that this H beta is real, then we would also observe all three blue shift, which is also common in AGN. So if we look where these sources I just showed you are located, we can see that they are exactly in the most overdense regions. So with this, we can see how the environment can affect the evolution and trigger star formation in galaxies as well as AGN. And with this, I'm going to finish my talk and leave you with a summary. And I'm happy to answer any questions.
Fantastic work. I'm having a hard time wrapping my head around the fact that those galaxies that you showed, they have an AGN, and this shift could be because of it seems that there is a merging system going on, maybe not for one galaxy.
Yeah.
So the shift and not having a broadband, I guess, it would be like two spectra from two galaxies. Also from the other one, I don't know what is this, how accurate did you detect the H beta on the other one, the broad H beta?
Yeah,
it
so
seems like the other galaxy that you said there is no H beta. To me, the spectra seems almost the same.
Yeah, so okay, like for this one, there are actually two different spectra, because in simple spectroscopy, like the observations are designed in the way that the light is dispersed in two perpendicular directions. And that's why for most sources, there are two spectra. And for this source, there are actually two spectra. And in both of them, there is a faint signal of H beta. And there's like on the combined spectrum, if you use both spectrum in both directions, it's even more evident. But for this one, the unfortunate thing is that there's like only on one of the spectrum H beta is visible, and this is because there is another source which is on the way on one direction. There is another source, so you cannot really use this part of the spectra with H beta. So this source, unfortunately, is not so clear. But I think because this point-like source, it's more like it's more secure that this is agent, because the O3 blue shift is a possibility, not necessarily, but even if we assume that there is no O3 blue shift, still we would see this point source.
Point source in 417?
Yes.
Isn't that the resolution of 417, which is a bit different from the other ones?
No. The narrow band it's not so deep as, for example, broadband. But I think that this point source, it's just the emission in the narrow band is dominated by the part of the spectrum which comes from the point source. So there is probably also some extended source, but it's just much fainter compared to the point source, so it's not visible in the narrow band.
Can you go on the plot of the dusty emitter?
Yeah.
So what is the luminosity of this galaxy, and can you exclude that there's, for example, an obscured AGN by the dust of the host galaxy?
I don't have a luminosity from top of my head, but I would say that like this is like difficult. Like you cannot really have a clear criteria like how to distinguish between this.
But the stellar population seems very blue. Doesn't necessarily mean much, but
do you have any information, or you plan to add other information for these resources in this survey, let's say, or maybe you searching in the archive?
So the problem is that if you look at how the survey is designed, here I skipped the slide, but the declination is 53. So
okay.
it's, there is no chance to get ALMA, but NOEMA is possible. So far, there is no observations for these sources.
Okay. And I didn't know this. So,
yeah.
Not my expertise, so maybe it's a trivial question. How do you get in the same environment, in same redshift, a very dusty star-forming object and a dust-free star-forming object?
That's a very good question.
Okay, so it's not
on which I actually don't yet have an answer.
there are examples in nature, but how to do it, it's
there are examples, but okay, in the same environment, because in this case, striking is like
I know examples at lower redshift, but I guess nature can do that. How? It's a question.
Okay.
Just
Related to the question, I mean, can you give an upper limit on the age of your galaxy, since you cannot see dust in one case, because since there is no dust, probably dust didn't have enough time to grow. And can you compare this age with the age of the other galaxy when you see some dust? I don't know if you have done something.
Yeah, I think this is a very good idea, but with the current data, I think the age will be very difficult to constrain, because the only constraint is from the set fitting, and it would be very uncertain. So I'm not sure how trustworthy this will be.
Questions from the remote? No.
A very quick one. I understand this is work in progress, but have you tried to compare with luminosity functions?
So I have a very preliminary luminosity function we can chat about later because
You can show me, but then you have to kill me.
yes. No. I didn't show the luminosity function because I'm still working on the completeness corrections, and I'm just at the moment not so sure about the completeness correction. Don't want to show the results I'm not sure about.
Yeah. There's no other question. We can thank you. So, we will see you in the next either